Okay, Chapter 4 is describing the relationship between two variables. Up until this point, we've really only been talking about one variable, say calculating the mean of test grades, or the standard deviation, or the things we can, the formulas that we've used thus far. We've just been looking at one variable. And this chapter, we'll be looking at two. So maybe does how many hours you study for a test have something to do with the grade that you made on it? The things you can look for in 4.1 are scatter diagrams, talking about the linear correlation coefficient, computing and interpreting the linear correlation coefficient, seeing if a linear relationship does exist between two variables, and then the difference between correlation and causation. There is something called a bivariate relationship, and it happens in real-world applications when two variables are related to one another. And we've kind of already talked about what a response variable is and what an explanatory variable is, but it's also called a predictor variable. Remember, I think of the x as your explanatory and the response as your y value, because it's like the y value responds to what your x value is doing. A scatter diagram, you may have heard of this before, maybe a scatter plot, is a graph that shows the relationship between two quantitative variables measured on the same individual. Each individual in the set is represented by a point on the scatter diagram. The explanatory is plotted on the horizontal axis, and the response is plotted on the vertical axis. I think of it as an XY coordinate, and it's pretty simple when you think about it like that, but we'll kind of take a look at what that looks like. So a pediatrician wants to determine the relationship that may exist between a child's height and head circumference. She randomly selects 3-year-old children from her practice, measures their height and head circumference, and obtains the data shown in the table to the left. If the pediatrician wants to use height as a predictor, head circumference, construct a scatter diagram. And so this would be your x value per se, and this would be your y. And so I'm just going to have to probably go over this really quick, but you'll get the idea. And these numbers are so small, I'll just kind of give you an idea of what it looks like. But let's see, the smallest height is 24.5, so it goes from 24 to about 27.75. I just don't have a lot of room on here, but of course you could count by, say, 0.5s to make it a little better. And then the heights, I will just do 17.2, 17.4, 0.6, 0.8, and then 18. But anyways, this is your height, and then this one was head circumference. And literally all you do, so for this one, I'd go over to 27.75 and up to 17.5. So over 27.75, that'd be about right here. And then I'm going to go up all the way until I get to 17.5. So that's between 6 and 4 here. So that plot would be there. And you do that for each of them. So I'll do a couple more. 24.5, 17.1, that's about here. And you'd keep going. I'm just going to do it randomly. And after a while, you might start to see a pattern. And we'll kind of talk about what those patterns mean. So there are different types of scatter diagrams. There are ones that look like they're going in a straight line and going up. Maybe they look like they're going in a straight line and going down. And so those have a linear relationship. There might be something that exists where it makes a little curve. That's non-linear. Or maybe this little lightning bolt looking thing. Or maybe there's just nothing going on at all. So those are either non-linear relationships or linear relationships. The only ones that are linear relationships are the first two, and we're going to explore a little more into those. Two variables that are linearly related are positively associated when above average values of one variable are associated with above average values for the other, and vice versa. Below average goes with below average values. So basically, when one increases, the other increases. So 8, keep going up, so on, so on, so on. And it kind of works backwards too. Like as these decrease, then these variables decrease as well. So basically, it always goes up when they're positively associated, reading it from left to right. And again, as one variable increases, the other variable increases. You also have a negative association that exists, and if this variable is increasing and it's going down, that means that while the explanatory variable is increasing, the response variable is decreasing, and it causes that relationship to look like it's going down. And that's a negative association. When one value increases, the other value decreases. So you can look at a relationship from a scatter diagram and gather a little information about what's going on there. But a little better way is through the linear correlation coefficient, also called the Pearson product moment correlation coefficient, and it just tells you how strong a line is and if it's positive or negative between two quantitative variables. The Greek letter rho represents the population correlation coefficient, although we don't use that very much in this class. What you really want to focus on is R. R represents the sample correlation coefficient. You need to remember that R equals correlation coefficient. So maybe I tell you, find the correlation coefficient. You need to think, oh, she wants R. And there is a formula for that. So this is one of the formulas. I don't use this formula specifically, but if you want to use it, you can do that. But I will not be explaining this one. I'll be explaining another one. But if you were to use this one again, you'd get the exact same answer. I use this formula, and it looks maybe a little more scary than the other one, but it's really not too bad. So correlation coefficient, R is equal to S sub xy divided by the square root of S sub yy times S sub xx times S sub yy. Well, what are all these things? To get S sub xy, we do the sum of x times y minus the sum of x times the sum of y divided by n. To find S sub xx, we do the sum of x squares minus the sum of x's squared divided by n. And to find the sum of y, we do the sum of y squareds minus the sum of y squared divided by n. I know that's a lot of information at once, but we're going to do an example, and I'll kind of show you how to do this. Before we actually find a correlation coefficient, let's kind of talk about what it means and what we might get. So R is always between -1 and 1. If it is +1, that means it's perfect and positive. It's a perfect line. And if it's -1, it's a perfect line, but it's going down. So really, anytime it's a positive R, it's going up. Anytime it's negative, it's going down. And you want to get close to 1 or -1. If you're close to 1, we have strong evidence to think, well, maybe there's an association between whatever that we're looking at. And if it's close to -1, we can say that there's evidence of a negative association between the two. The closer it gets to 0, the closer, the more spread out it gets, And the more we can kind of look at this and say, well, maybe they have no relationship with each other. So anytime you represent R, you don't have to put a unit with it. It's unitless. And the correlation coefficient is not resistant. So these are examples. This is R equals 1. It's a perfect line. And then as it gets a little away from 1, so maybe 0.9, it gets a little farther away, a little more spread out, but it's still got a relationship. You can still tell that it's going up. This could really be anywhere from 0.7 to 0.9 positive. They all kind of look like this. As it gets farther away from 1, it gets more spread out, but this is a strong relationship. This one you can still tell it's going up, but it's still getting more spread out, and so we could say an R is approximately 0.4. You could say it's 0.5, 0.6. That would be okay too, because you're kind of saying that it's not strong, but it's moderate. In the exact same situation with it being a negative relationship, perfect line going down is R -1. As it starts to get spread out, we can still say it's going down. It's still pretty compacted, so it's approximately -0.9, maybe -0.8. Starts to spread out. It gets closer to 0. Still kind of negative. We can still tell it's going down. But G, I can't even tell if it's going up or going down. We would say our relationship is pretty close to 0. There's not a whole lot going on here as far as this relating to that or whatever it is that we're looking at. And this is one of the ones that I showed you. This definitely has no relationship either. Even though it looks like a rainbow, we're looking for linear relationships. So let's find the linear correlation coefficient. So you will be given 2 variables, an X and a Y, sometimes with context. This time we're not given context. We don't know what the X and the Y are, but that's okay. And then when you see correlation coefficient, you need to know that we're finding R. So that's that long formula, right? That's okay. So here we go. When I'm given an X and a Y, but I need to do other things. I need to find a couple new columns. So I'm going to find X squared. I'm going to find Y squared. And I'm going to find X times Y. And I'm going to do that because that is part of my formula. And I'll show you what that is again. And then I want to find the sum of all of these. And remember, the sum is I'm going to add them all up. So 10 plus 8 plus 7, 6, 12, 10, 5. The sum of those are, or AKA the sum of X, is 58. If I add up all my Y's, I will get 50. That represents the sum of my Y. I'm going to square my X's. So remember, to square is to multiply it by itself. So 10 squared is 100. I'm looking at the X values. 8 squared, 64. 49, 36. 12 squared is 144. 10 squared is 100. 5 squared is 25. Add up all those, 100, 64, 49, 36, 144, 100, and 25. I will get 518. This is the sum of my X's squared, sorry. I'm going to do the same with my Y's now. 6 squared, 36, 8 squared, 64, and so on, until I am done. I'm going to add up all of the Y squares, and I'll get 386. The last step is I'm going to multiply my X times my Y. So 10 times 6, my originals. 8 times 8. 7 times 8, right? Each X and each Y for whatever column or for whatever row you're looking at. 6 times 9, 12 times 4, 10 times 5, 5 times 10. we're going to add up every single one of these as well. 60, 64, 56, 54, 48, 50, 50. You will get 382. That is the sum of my x times y. Now, all these down here, you may say, well, that kind of looks familiar. And you may be saying this because that's what our formula says to do. And so I'm going to erase this. So if you need a second, pause. And I'm going to take all these numbers. I'll write them again. And we will go from there. So I'm going to write them up here. My sum of x was 58. Sum of y was 50. Sum of x squared was 518. Sum of y squared was 386. And sum of xy was 382. Now we're trying to find the correlation coefficient. So I'm going to write that formula again. It's r equals s sub xy divided by the square root of s sub xx, s sub yy. Now, before we can plug anything into these, we have to remember that each one of these kind of has its own formula too. So I'm just going to do it one at a time. S sub xy is the sum of xy minus the sum of x times the sum of y divided by n. We can find a lot of these. We've already found them. The sum of xy is that 382 times the sum of x times the sum of y. But we don't know what n is. N is the number of pairs. So we have 1, 2, 3, 4, 5, 6, 7 pairs. So I'm going to go ahead and put 7. When you put this in your calculator, you should get negative 32. Negative 32.28, 0.2857, sorry. Okay, so you've basically, let me rewrite that 7, that's not very good. You've basically found the numerator of your correlation coefficient. And this numerator will tell you basically if this is going to be a positive or negative association. So because this is a negative 32, we're going to end up having a negative association. So I'm going to go ahead and put that up. Sorry. I'm going to go ahead and put that up there. Try my best. I may have to abbreviate just because I'm running low on room. I may have to, that eraser is not very big. May have to erase all of it again. Sorry. Maybe. I can kind of get by with it. All right. We'll try our best, right? Okay. So now I need to find S sub XX. So S sub XX is the sum of your x squareds minus the sum of your x's squared divided by n. There is a difference there. The sum of x squareds was when we squared them and then added them together, and that's that 518 number. Minus the sum of your x's was just when we added the x's together, and then we're going to square it, and divide by n is 7. When you put this in your calculator, you should get 37.4286. And I put it in my calculator like that, but when I put it in this formula up here, I'm just going to write 37 because I'm running low on room. See if I can do this again. I apologize. I'll write the next one in green so it's a little easier to see. I need a better eraser. Okay, so the very last one is S sub YY. S sub YY is similar, except we are going to use our Y values. So you find the sum of Y squared minus the sum of Y squared divided by N. When you do this, you will plug in the sum of Y squared, so 386 minus 50 squared divided by our 7. Simplify this, put it in your calculator, you'll get 28.8571. I'm just going to put 28.8 in my formula up there. I'm just going to put what my R equals. So plug it in, all in your calculator. Be careful about that square root. When I plug all this information in, I get negative 0.9824. So there's a negative relationship, but it's pretty strong because it's pretty close to 0. So there's basically another way to kind of check that your correlation coefficient does represent a good linear relationship. And so you find the absolute value of the correlation coefficient, which basically means if it's negative, make it positive. And then you look at this table to your right, depending on your sample size, and you want to know if the correlation coefficient, the absolute value, is greater than the critical value. We say there is a good linear relationship. Otherwise, it doesn't. And basically what this means is if you only have 3 pairs, you should have a very high relationship. It's basically saying the more pairs you have, the more wiggle room you have, right? It kind of goes down, but it's just another way for you to check to make sure that you got a good relationship. So let's try that for ours. And so we had a N of, let's see, the one that we just did, our N was 7, and our R was negative 0.9824. So if I take the absolute value of that R, that's what those little wall-looking things mean, the absolute value, I get positive 0.9824. If I'm looking at an N of 7, that's all I care about. My critical value is 0.754. And I'm going to compare that to my R. And I look at the two, and I see that my R is greater than that critical value. And if that is the case, then we can say a linear relationship exists. Okay, I'm going to let you go back to example 1, and you can create this relationship yourself, the correlation coefficient, and find your R. And I'll just go ahead and tell you what it's going to be so you can kind of check. I got 0.9111. And so it's pretty strong and positive. And then it says, does a linear relationship exist? So we can check that table. And for my critical value, I got 0.602. And 0.9111 is bigger, so a linear relationship does exist. According to data obtained from the Statistical Abstract of the United States, the correlation between the percentage of female the female population with a bachelor's degree, and the percentage of birth to unmarried mothers since 1990 is 0.94. Does this mean that a higher percentage of females with bachelor's degree causes a higher percentage of birth to unmarried mothers? That is something we will look at. Definitely not. The correlation exists only because the percentage have been both of the percentages have been increasing since the 90s. So you have to be careful about something like that happening. This causes a high correlation, and sometimes even though you have a high correlation, doesn't mean that this causes this or that causes that. So you have to be careful. We cannot claim a causal relationship that exists between two variables. We can only claim causality when the data are collected through a designed experiment. The reason that is because there are situations that could arise, say, lurking variables, which we talked about in Chapter 1. And remember, lurking variables are those variables that you don't maybe think about or you're not considering in your study that still exist. So ice cream sales and crime rates have very high correlation. Does this mean that the local government should shut down all the ice cream shops? No, because we know that they most likely, one isn't causing the other, but the reason they have such a high correlation is because they both go up because of the temperature. As the temperature rises, ice cream sales and crime rates rise. So the lurking variable in that situation would have been temperature. Okay, I'm going to read this to you, but I went ahead and found the R for you, the correlation coefficient. It says because colas tend to replace healthier beverages, and colas contain caffeine and phosphoric acid, researchers and Catherine Tucker and Associates wanted to know whether cola consumption is associated with lower bone mineral density in women. The table lists the typical number of cans of cola consumed in a week and the femoral neck bone mineral density for a sample of 15 women. The data is here, and so we took all these variables and we found our correlation coefficient, which is on the next. So we found that the correlation coefficient was negative 0.86. If we test our critical value, that means that a negative relationship does exist. But can we conclude that an increase in the number of colas consumed causes a decrease in bone mineral density? So can we say that this causes this, or are there some more things going on? So think about possibly some other things other than Coca-Cola that could affect bone mineral density. Here's a scatter plot just if you want to see it, right? It does look like there's a nice little relationship going on. It's going down. It's got a negative relationship. So as you consume Coca-Cola, your bone mineral density goes down. But we see here that there are some other things that could affect bone mineral density. And those include, but are not limited to, BMI, height, smoking, your alcohol consumption, your intake of calcium, and your physical activity. So basically, the moral of this is you have to be really, really careful about saying this causes that, or just because you drink Coca-Cola, your bones are going to get more dense. And so they were careful to say that an increased cola consumption is associated. That word is important, associated with lower bone mineral density because of lurking variables. You can't say that this causes this a lot of the time unless you consider every single lurking variable, which is very hard to do. All you need to know is just because they're associated doesn't mean that it causes it. Association does not imply causation. 4.2, we are talking about the least squares regression. So we're going to figure out how to find that least squares regression line and use that line to make predictions. figure out what it means, the slope and the y-intercept mean, and then compute the sum of squares residuals. Excuse me. Okay, so here we have an x and a y and values that go along with each. And our R for this is 0.9477. It was given to us. And we're going to keep looking at this example in the next couple slides. But be keeping this in your mind while we kind of talk about what we're going to be doing. If you took algebra, sorry this kind of zoomed in, but I'll tell you what it says. This is the equation that we're going to be using. And M represents the slope. So the steepness of a line. And B represents the y-intercept. So where it goes through the y-axis. Anytime you have an x value of 0, that y value is going to be your intercept. So if I were to say find a linear relationship that relates x and y, x being the explanatory variable and y being the response variable, by selecting 2 points and finding their equation. If you took an algebra course, this is what you did in algebra. You basically found on average how steep is this line, or where does it go through the y-intercept. So you can pick any 2 points that you want. Let's say we choose this x and y pair and this x and y pair. The 2 points that you choose have to be a pair. And we can use the equation to find a slope, which is y2 minus y1 over x2 minus x1. I can call 5, 7 my y2, so that means the x is my that 2 is my x2. And then I can say 1.9 is my y1, so that means that 6 is my x1, and plug it in, and we get that value for the slope, negative 0.95. So we're going down, we have a negative slope. And then if I actually want to find an equation, I can use this formula. And I can plug some random values in for y1 and x1. I say some random values, a coordinate pair in your example. So I chose 2 and 5.7 again. So plug it in and solve for your y, and you will be given the equation. So we can find points and find an equation that fits this line to the best of our ability. Once you have an equation, you can plug in x values to predict what your y is going to be, whatever that may be. So let's say I want to predict y if x is equal to 3. Plug in 3 for x, simplify, and it's saying when x is 3, we predict my y to be 4.75. And so that's kind of what we're going to be doing a little bit today. Let's say that even though I predicted when I plugged in x equals 3, I got 4.75. On my actual table, the 0.35.2 existed. So why would I get 3.75? Because that's what my equation, 4.75, because that's what my equation predicted that I would get. The difference between that observed and predicted is called a residual. So that residual is the distance between your observed and predicted. And I like to use a car example a lot. So let's say that you take your car to the dealership and they tell you this car is worth, say, $500. I'm going to draw a little dot. How much they think it's worth. But you go out and sell it, and you sell it for $400. So that's a residual. You made $100 less than what they thought you were going to make. But the opposite could happen. You could make, sell it for $600 when they thought it was $500. So your residual is positive $100 because you sold it for $100 over what they thought you were going to sell it for. So the least squares regression is the line that minimizes the sum of the squared errors or residuals. And that line minimizes the sum of the squared vertical distance between the observed values and the predicted values, kind of what I was just telling you about. And that is called y hat. And it looks like minimize the sum of residuals squared, or the squared residuals. Okay, it says the equation of the least squared regression is given by, I am not sure what's happening to all this formatting, but I will definitely write it for you. It looks just like that line we looked at earlier, but it's basically specific to a least squared regression. So it says y hat is equal to b sub 1 times x plus b sub naught. We can get b sub 1. I'm going to write this in green just so I can see it a little better. We can get b sub 1 by finding s sub xy divided by s sub xx. We can find b naught by finding y bar, the average of y's, minus b sub 1 times x bar, the average of the x's. I apologize. I don't know why it is being formatted in this way, but all this says is y hat is just an estimation of the mean. The mean value of the response variable for any value of the explanatory variable. But really the main thing here is y hat is an estimate. And so it gives you an idea of what it's going to be. And it could be that, it could not be that, but it's basically giving you, on average, this is what we would expect to happen. Okay, so let's actually find a least squares regression line. And so in order to do that, we're going to have to use that formula that we saw earlier. Y hat equals b sub 1x plus b sub naught. To find b sub 1, we're going to do s sub xy equals s sub xx. That's the same formula that you use whenever you found the correlation coefficient. And so you're going to use that formula. And when you do that, you will get 2.1886 divided by 11.9773. So I actually end up getting 0.1827. So that's my B naught. Now I'm going to have to erase this to fit all the other information on here. And so just be ready for that. So we know that B sub 1 is 0.1827. To find B naught, we have to do y bar minus b sub 1 times x bar. And so we've already got b sub 1, but we have to find y bar and x bar. And remember, we've talked about x bar before. It was just the mean of all the x values. But we've got two now. We've got an x and a y. And so we're going to add up all those values for x and get 291 and divide by however many there are, in this case 11. And so basically the average height is 26.4545. But I only have room to write 2 decimal places. To find y bar, we're going to add up all those y values, and you'll get 190.6 and divide by 11, since there are 11 circumferences we're looking at. And when I simplify, y bar should be 17.3273. I only have enough room for 2 decimal places. And so what we're going to do next is we're just going to plug everything in. B naught is 17.32 minus that b sub 1.1827 times x bar, which is 26.45. When I simplify all that, I get b naught is 12.4941. 12.4941. And so now I have everything I need to have my equation. And so I'm going to erase all this again and plug in b sub 1 and b naught. So, and I'm going to write it up here, and I'm going to write it in green. Y hat is equal to 0.1827x plus 12.4941. And it says predict the head circumference for a 3-year-old with a height of 27 inches. And so basically your x is equal to 27. So I'm going to plug in 27 for that x. 0.1827 times 27 plus 12.4941. And for my y hat, I would get 17.429 inches. So when I have a kid who's 27 inches tall, I expect them to have a head circumference of about 17.429. It says if the observed head circumference for a 3-year-old with a height of 27 inches above or below average. So this y hat that we just found, that's the average. And it's saying for our child, are they above or below average? So we're looking at the head circumference. We're looking at that 17.5. And because it's bigger than that 17.429, it is above average. It says draw the least squared regression line. I'm going to kind of show you what that looks like on another slide, so I'm not going to do that right now. But an idea of what it looks like would basically be it starts at about 12 and it's a positive point, starts at about 12, and because it's a positive slope, it's slowly going to be going up. This says for a slope of b, we will say that each unit changes in the explanatory x, we expect for the response variable y to change by that many units. So basically, again, kind of like I was talking about, a slope is the steepness of the line, how far up you're going, or the ratio of how far down you're decreasing. Another thing you need to know about slope is sometimes it doesn't really make sense, and so it is a place to start your line, but for example, in our last one, when we had a y-intercept of 12, that b naught, it doesn't make really any sense to say for our x values when a child was 0 inches tall to have a height of a head circumference of 12 inches. That doesn't make any sense. And so sometimes the y-intercept is really not applicable to what you're talking about, but it is, again, a place to start. So I just did this actually on the previous slide accidentally, but same thing, just because it is, let's see, plus 12.4941. That 12 number is your y-intercept, and because it doesn't make any sense when x is 0, it is not applicable. You have to be really careful to not extrapolate which basically means you can't go out of the scope of your model. We looked at children that were basically between the height of 24 and 27.75 inches, I believe. And so what this means is I can't make a prediction about a child who's 30 inches tall because we didn't look at anyone who was 30 inches tall when we created our line. Here's just another example. If you want more practice, I'll give you the answers. The correlation coefficient, or the R, is 0.8287. And the regression equation is y hat. I'm going to put that down here. Is y hat is equal to 15.8932 x plus 140.0838. And you can answer questions about this if you want to do another example. Okay, 4.3 talks about basically how do we know that our models are good, and so we can kind of look at diagnostics on the least squared regression line. And so we're going to talk about what the coefficient of determination is and perform a residual analysis on a regression model and look at influential outliers. So the first thing you need to know is that the total deviation is your y minus y bar, so your y minus your average, basically. The explained deviation is y hat minus y bar, and the unexplained deviation is y minus y hat. This is just a graphical representation of what I was just explaining, but the blue is our predicted line. The y bar is your average, and then it just shows you what it looks like to have the total deviation, explained deviation, and unexplained deviation through a picture. It also, this shows you how you could find the total variation. It's the sum of the unexplained variation plus the sum of the explained variation. And this is how you would do it, although we don't do that this much in this class. But just so you know, this is how you would find the variation if you wanted to. Okay, so the coefficient of determination sounds like correlation coefficient, but it's a little different. And I'm not sure what's going on with the formatting of my PowerPoint, but this should be R squared. So all these should be R squared. And it can also be little r squared, but it basically is very similar to the correlation coefficient, but it's got one big difference, and it's just that. It's the correlation coefficient squared. And the difference between those two also is that r is between -1 and 1, and r squared is just between 0 and 1. And the closer it gets to 0, we can say it has no explanatory variable. And if it's closer to 1, we can help kind of explain some of the variation that's going on. This is kind of how you find the total variation, maybe how we find this r squared formula. This is something I wouldn't worry about too much because I'm going to show you how to do it. So, like I said, r squared is the same, big R squared is the same as r squared. And you literally just square what you got for the correlation coefficient is what that says. Sorry about the way this is looking. Correlation coefficient. And we just square it. And it is r squared, so it's pretty self-explanatory. Okay, so this says determine, here's our, still our head, height and head circumference example. And recall we got r equals 0.911. And it says determine and interpret the value of the correlation of determination when height is used to predict head circumference. So I am going to square 0.911. And when I square that value, I get 0.8299. What this means basically is, I'm going to turn this into a decimal. A percentage. And what this means is 82.99% of the time, or basically 83%, we can say that height does affect head circumference. And then that extra 17% is just unexplained, maybe other things that affect head circumference. But we can actually put a percentage to how height affects head circumference blank percent of the time, and so that's pretty cool. So I want to show you some pictures, some scatter diagrams that go along with this data. Please notice that all the y values are the same for each one, and the only thing that's changing is the x value. So we're seeing how x affects y, and so in each one of these you'll see some differences. Data set A was almost perfect. 99% of the time we can basically say that x affects y. In B, they're a little farther apart, so it's a little farther away, but 94% of the time we can say that x affects y. And then C, it's really spread out, and our r squared was only 9.4, so we can really only say that 9.4 of the time x affects y, which is not very much. We've talked about residuals a little bit, but residuals do play an important role when you're seeing if it's a good linear model. And residuals are really good when we want to see the relationship between a predictor and response variable, determine the variance, and if it's constant, and to check for outliers. A lot of the times when you do this by hand, it's very tedious, and so a lot of statisticians will use technology. Remember that the residuals is y minus y hat, and we're going to see kind of what that looks like when we put it on a residual plot. And basically, remember the residual, like let's say this is my line. My y hat is the one on the line, and my y is what I actually got, so how far away it is from the line. A residual plot basically takes what a linear model used to be, and then it puts it horizontally, basically. So let's say that was my line, and then I wanted to do a residual plot, so I'm going to kind of turn it to where it looks like this pink line. And so it's when we do this, it's easy for us to see how far away the residuals are, kind of all in the same playing field. So the green lines are residuals. It's how far away. And what you want it to look kind of scattered like this. You don't want B. You don't want it to look like this. Like on the left side, they're all high. And then in the middle, they're all below. And then on the right, they're high again. This doesn't look very good. You want it to look like A. You want it to look scattered. So I'm going to show you... for this data, we looked at amount of radioactive material remaining in a sample every day for a week, and how much it weighs afterwards. So this is what the data looks like on a scatter diagram, and the linear correlation coefficient is negative 0.994, so pretty good, right? If we draw a line, it looks like that. And basically, we want to do one more thing to see if it's appropriate. We can say, this looks pretty good, but let's put it on a residual plot. And what we want is we want it to look scattered. So if I put that on a residual plot, if I turn that axis to be, that line to be more horizontal, just like that, that's my line. I didn't do a very good job just now, but they're not very good, right? This is not very evenly distributed, and it's not very scattered. If it looked more like that, maybe, but this is not a very good linear model, and so because of this, we cannot say that the linear model is appropriate. There's something that exists called a constant error variance with residuals, and that basically happens when we constantly, I mean, it's pretty self-explanatory. It's a constant error, and it gets farther and farther and farther away. And this essentially happens when the residuals are increasing or decreasing as the explanatory variable increases. And I'll show you kind of what that looks like. So this is an example of when that happens. They started out kind of around -1 and 1, and they just keep getting bigger and bigger and bigger. You don't want it to look like a cone. It's not consistent at all when you do that. You want it to be consistent. You don't want it to keep the residuals to keep growing, because in that case, something's going on. A plot of residuals against the explanatory variable may also reveal outliers, and residual plots are very useful when looking at outliers. And so we'll kind of look at that. So as you can see, we can kind of see the outlier here, but then when we put it on a residual plot, we can see really how far away it is. It's a lot more obvious. And also box plots, residuals are good for looking at in box plots because it's kind of easy to see the outlier. We are not going to do this because I do not have you in class. Influential observation is an observation that significantly affects the least squared regression line, slope, and/or y-intercepts, or the value of the correlation coefficient. So you got to be really careful about those outliers. So influential observations exist when the point of an outlier is relative to the values of the explanatory variable. So 3 could be really, really an influential point because it's going to be pulling this data down instead of where it wants to be going. Influence is affected by 2 things. The vertical position of the observed residuals and the horizontal position of the observation, also known as the leverage. So suppose an additional data point is added to the pediatrician's data. The child is 18 inches tall and has a head circumference of 16.5. When that happens, it affects your y value, it affects your r squared. I mean, it affects everything and not in a very good way. If you have influential observations, a lot of the times that you want to do is you just need to collect more data. That's always kind of a go-to, so maybe it's not hurting you as badly. And then there are techniques to reduce the influence of influential observation. And this is what statisticians do, but you don't necessarily need to know it for this course. So that is chapter